Okay, this is our introduction to HotSpot internals session, and this is intended for people who have the foolish notion of going and digging into HotSpot code. And the hope here is that when you come out of this session, you'll at least have some handholds, some familiar places to go to as you start looking at the HotSpot code. This particular session comes out of my own experience of joining the JVM Sustaining team at Oracle and being in the difficult position of having to fix bugs in HotSpot without having any experience and hitting a very large code base and trying to figure out exactly how the crazy thing works. So from those difficult experiences, I'm hoping to give you guys something a little better to start with. A little bit about myself. My name is Paul Nauman. I work for Oracle. I'm part of the JVM Sustaining team. We fix bugs in Hotspot and JRocket, our two JVMs. I have a longer experience in telecommunications. I spent a great deal of time at Bell Labs and Bell Corp and Ameritech, and a somewhat shorter period of time in financial services, all with sort of system-level, real-time software kinds of programming. So that's how I got into Oracle. Okay, as I said, the hope is when you come out of this, you'll have some sense of how the HotSpot code is laid out, some familiar places to go to, some of the important files, some of the important definitions that are in there, some of the important algorithms and data structures that are defined. And we're going to focus on what we in the HotSpot development team call the runtime, which is basically if you take away the garbage collectors and you take away the compilers, runtime is everything that's left. So the interpreter, the class loading stuff, the threading system, all three of those you'll learn about today. But then there's a whole bunch of other miscellaneous stuff that's in the runtime as well. Okay, so here's what we're going to talk about. Just went through the introduction. We're going to do a summary of the JVM model. So this really is a summary of the JVM specification. And the hope is here that we'll all come to a common understanding of what JVM is and what it does, and give you a little peek under the hood of what it has to do internally in order for it to work, and then we'll delve into that deeper. We'll do a little section here on Hotspot source code, how it's laid out. And as part of that, there were also a couple of code patterns that are used extensively in Hotspot that I thought it would be a good idea to alert you to, so that when you run into them and you're browsing Hotspot code, they don't throw you off track. There's some interesting stuff going on. And then the three primary parts of the talk here are again, the three parts of the runtime that we're going to look at. Class loading and metadata. Metadata is basically the data that Hotspot stashes away as it reads in classes, which it needs to organize in a particular way in order to be able to access it in a very efficient manner so that we can execute very quickly. Template interpreter is the interpreter that Hotspot uses. It's a little different than interpreters that you may have come into contact with before, and we'll take a look at that. And then finally, we'll do a little bit on the threading system that Hotspot uses. Okay? All right. So, JVM, what does a JVM do? So from a 30,000 foot level, this is the model that we're all familiar with. So we have source files, typically Java, but not necessarily always, that get fed through a compiler and generate class files. And class files are the basic input to the JVM. So when we start a JVM by doing a Java command on the command line, and we specify our class path and our starting class, the JVM actually looks for those in the file system, finds them, and starts executing them. And that's what leads into that's what starts off the whole class loading process. So here's a little closer look at this. On the left, we have a Java source file, which is a text file. Java source file contains one or more class definitions. Each class definition leads to a class file being created. And here are the language features on the left and how they get encoded into this class file, which is a binary file on the right. And again, all this stuff is laid out in the JVM specification. I'm not going to go to it in too much detail. Just suffice it to say that all of the pieces that are part of a typical Java program, class and interface definitions, super interfaces or implementation of interfaces, field definitions, method logic, and references where you reference to external classes or external methods. Those all get stuffed into this class file in a rather compressed format. And again, that's the basic input to the JVM. So what the JVM specification tells us to do as a JVM implementer is to read these binary files in somehow, stash the data away in a manner that's convenient for us so that as we start executing our program, we can go to it in a quick manner, and we'll see how that's laid out. These are the 4 phases, at least according to the JVM specification, of preparing a class for execution. The first thing we do is what we've just been talking about, which is to load the file itself. We pull in the binary data, we parse it out into its various components, stash it away in convenient data structures. We go through a process called verification. I'm not going to go into this in any depth. It just basically takes a look at the classes that we've just loaded and make sure that they're not going to violate the integrity of the JVM. So things like stack underflows, type mismatches between what's expected to be on the stack and the operation that's going to occur at a particular point in time. That's basically what verification does. Linking is the process of taking those references that we have to methods, fields, and classes and actually finding inside the JVM the class structures that they refer to. Now, the JVM specification gives us a great deal of latitude as to how and when this is done, from 2 very great extremes. On one extreme, you can do the linking as soon as you load in the first class. You could transitively or recursively look at the classes that it refers to, load those, look at the classes that they refer to, load those, etc., until you've loaded the entire program, and that would be a static linking model. Hotspot is at the other end, where we basically don't do any linking or resolution until that reference is actually used while executing. And then we go and we look, okay, do we actually have that class loaded already? If not, then we need to load it, and so on. Finally, having done those things, then we go through the static initializers for the class that we've loaded. Again, this is behavior that's specified by the JVM specification. Okay, so this is a Java thread. The JVM spec says a Java thread is basically just an ordered list of Java frames, and a Java frame has to have the information that's shown here. And again, this can be stashed away in an implementation-specific manner. So you need to know the current method that you're executing. You need to know the class that method is part of. You need to know the bytecode that we're currently executing. There's an array of parameters and locals, so the parameters that are passed into the current method, and the local variables or local variable slots that are needed during its execution. And then finally, some sort of representation of an operand stack, since the bytecode expects that this is a stack-based machine or stack-based model. So just to work through a couple of these examples, if we look at the new bytecode, the bytecode that tells the JVM to create an instance of a class that we've loaded. So here on the left, we have an array of bytecodes that we're churning our way through. We hit this new bytecode, which is followed immediately by 2 additional bytes, which is a 16-bit index into the constant pool that we've loaded with this class. We go through that constant pool a couple of times, and that ultimately resolves out to a string that represents the class name that we're referring to. So that's the class that we're going to create an instance of. Similarly, there's 4 field access bytecodes: get field, get static, put field, and put static. And these work in a very similar manner. We have a stream of bytecodes over here on the left that we're executing through. We hit one of these bytecodes. It's followed by a 16-bit index into the constant pool. We go through the constant pool a couple of times. There's some internal references. And we end up with 3 strings over on the right: the class name, the field we're about to access, and the field descriptor, which you're probably all familiar with, is a string representation of the type of that field. And again, similarly, when we're invoking a new method, invoking static invokes a static method, invoke virtual and invoke interface. I won't go into invoke dynamic, it's a little bit different. But basically, we hit one of these bytecodes, there's an index into the constant pool, we resolve through the constant pool and find 3 strings. So in all of these cases, then the JVM has a string as the output of these operations, and it has to figure out how to find the thing that that string refers to, and that's that linking operation that I mentioned earlier in part of class file preparation. Okay, and then just a very brief description of the heap. Everybody knows what the heap is. This is what the JVM says it's supposed to be. And you can tell by this description that, again, we have a great deal of latitude as to actually how we implement this. The heap is just where all the objects are kept, all the class instances and Java arrays. It's created as the JVM starts up. It's shared among Java threads, maybe expanded or contracted as needed. And then finally, and this is where the greatest latitude is given, somehow and at some point in time, objects or unused objects need to be tracked down and reclaimed. Now, as in HotSpot, we try to do this very efficiently so that this should happen concurrently with your program execution so that you don't have to stop and do this. A perfectly valid implementation, at least according to the JVM specification, is to run all the way until you run out of memory and then stop the whole thing and find the unused objects and then start it up again and do that until you run out of memory again. That's a valid, although particularly not useful, implementation. Okay, so let's take a quick look at Hotspot Source. Excuse me. So Hotspot Source is kept on the java.net website, the OpenJDK, and you can, if you're looking at Hotspot, you can choose to download the entire JDK. I personally recommend against that because there's just so much in there, a whole bunch of stuff that you're not going to need. You can, in fact, download Hotspot only, which is shown in the second line here. These are all Mercurial repositories, so those tools are readily available. Here's a diagram of how this stuff is all laid out. JDK root is all of these bold rectangles here. Those are all independent Mercurial repositories. Each of them has a directory tree or represents a directory tree within it. The Hotspot has its own repository, so again, you can pull that down all by itself. There's directories underneath that. We're going to burrow down just a little deeper. So the source directory under Hotspot has got 4 subdirectories. First one is CPU, and that contains source files that are specific to a particular hardware architecture, SPARC x86 or 0. The OS subdirectory has files that are specific to a specific OS platform. OS CPU are those that are specific to a combination of those. And then finally, the share directory is the one that's most interesting because that has all of the Hotspot code that is shared across all of the platforms. And that's the major place for all of the Hotspot common code. So in the VM directory, subdirectory of that, you'll see these directories. And I've highlighted 4 of these here in red because those are the places where you should probably go to find the most interesting pieces of Hotspot code. So class file stuff has all this class loading stuff, which we just talked about and we'll talk about further. The interpreter directory has got all the stuff in there for the template interpreter. The oops directory has the definitions of the classes that represent Java classes. We'll get into that a little more, as well as some other interesting definitions. And finally, the runtime directory, among other things, has got the thread system files stashed away in there. So if you're going to start out browsing, those are good places to start. Okay, I warned you about this. Common code patterns that are used in Hotspot. So the C and C++ preprocessors allow us to use macros. Often those macros are just static, but macros can also be functions. Macros, and the functions expect a parameter, and those parameters to those function macros can also be functions, and Hotspot takes advantage of that quite extensively. So here's an example, which I'm not sure how familiar this is to any of you guys, but here's an example that hopefully will bring it to light. So in the top left, we define a function, a macro function called colors, which expects as its single parameter f another function, which it then applies to these 3 strings, red, blue, and green. So after that, we now define a new function, g, which expands its single parameter x out to its parameter followed by a comma. So here we can take advantage of that G function in enumeration by simply using that color parameter, giving it the G function that we just defined above it. And so now this enumeration definition becomes legal because it's got all the strings separated by commas. Similarly, right below that, we can define a new function H, which, if you're not familiar with the way the preprocessor works, that hashtag X actually expands out to the string X with double quotes around it. So now we can define an array of strings which represent all of these values, red, blue, and green. And that allows us to do something like this little chunk of code here. We define a variable called font color. It is the type, the enumeration type that we've just defined on the left. We somehow put a value in there. And then suppose we're doing some debugging, we can actually do this print statement here, where we actually use this string, color strings, which is defined down here in the lower left, and give it the enumerated type font color, and that'll all work, because we'll actually pass it, the color strings will actually resolve to a string indexed by this enumerated type. Make sense? I'm getting some no's. Okay, that's not good. Okay, we're going to have to come back. Sorry. Another common pattern that is used takes advantage of the scoping capabilities of the language and the constructors and destructors that are part of C++. So, for example, here we have a resource pool called Handles. And as we start out this little block of code, this could be either an entire method, or it could be a sub-block within a method, or an if statement, or a while loop, or something like that. And at the very top of this, we define a handle mark, or some sort of mark, which basically marks a place in that resource pool where we've started. Now then we can then allocate resources out of that pool. In this example, we're allocating a handle, which is a pointer to an object. And then we can do something with that. Here we've found an object and we're going to print something out about it. But then when we hit this lower curly brace, then the destructor for handle mark is called, and that will actually release all those resources back to where they came from. So that resource pool will return to the state it was in before we entered this block of code. Okay, now I'm getting some good nods. Good. Okay, another thing that Hotspot does, which might be a little bit strange to people who program in C++ quite a bit, is taking advantage of the fact that we never have to be more than one platform at a time. The same JVM never executes on more than one platform. So instead of creating subclasses of a given larger abstract class to represent different platforms, instead we do these kinds of crazy include things where we define a class, but we suck in files that define platform-specific behavior for that class. The net result of that is there are places in Hotspot where a given class can have, I won't say widely different, but some significant differences in how it functions and what it does from one platform to the other. Okay? So those were some gotchas. Here are some important files you might want to look at as you're browsing Hotspot code. This globals file, as you might guess, contains a lot of global definitions, but probably the reason that I go here most frequently is because it has a complete list of all the command line flags that Hotspot understands. They're grouped into categories: development only, experimental, production, etc. But each of them has a little string. It's about all the comments you get here that describes what it does. But the nice thing about that is having found one of these flags, which does something interesting, you can then start text searching through the rest of the code to see, okay, so where is this flag actually used? What does it actually do? The next line there, the class structures, those are in that oops directory that I mentioned earlier. So those are some of the basic structures that represent Java classes in instances of C++ classes. Okay, so that's a good place to look, is class.hpp, and there's several subclasses of that. And then finally, these last three are interesting because they define the stack structure that the interpreter uses from one platform to another. They're slightly different. But that's a neat place to look. So if you're sort of stepping through the interpreter and you want to know exactly what the stack layout is at any point in time, you can look in these files. Okay, so now we'll get into the real stuff. So class loading proceeds pretty much as you would expect, and as the JVM specification says. And here, the only difference here is that I've actually filled in the actual names of the data structures that Hotspot uses to stash away this information. So because this is a loaded class, the C++ class that is used to represent it is a class called instance class. It has a reference to a constant pool. A constant pool, we divide the constant pool into two pieces. So there's a piece of the constant pool that captures the static information that's loaded from a class file. And then there's a constant pool cache, which is basically the pieces of the constant pool that we've resolved already, particularly linkages to other classes and methods and fields. And so as we're searching through the constant pool cache, as we're executing bytecode, we'll first look in that cache and see if we've already resolved that. There's an array of methods that are defined. The method structure is divided into two classes, one called method, one called const method. And const method basically has all the parts of a method, the data parts of a method that don't change, in particular the bytecode. And then the method structure itself has got all kinds of other bookkeeping information in it. Number of times it's been invoked, whether it's been compiled, etc. Okay, so that's the translation between those class files and the metadata that's kept by Hotspot. Here's our metadata hierarchy. So again, there's an abstract class called metadata. Abstract C++ class. One of the tricky things in talking about this is distinguishing between C++ classes and Java classes. Metadata is a C++ class. It has multiple subclasses. The ones we just talked about, method and constant pool. And then here's this little class hierarchy here over on the right. And these three subclasses in the blue box represent all of the possible classes that a Java object can be in Hotspot. So an instance class is an instance of a class that has been loaded. So it's basically a user-defined class. An object array class is an array of pointers to some other object. So those are not necessarily defined by a class file. In Java, you don't do that for arrays. And then there's a type array class, as we call them, which is basically just an array of primitive types. There's a parallel hierarchy for OOP, which is called OOP-desk, and this is basically C++ classes that represent the object layout for these specific classes or class types. So an instance OOP-desk is a C++ class that represents the way an instance object is laid out, so the fields that we reference as we execute our Java program. Okay, and this is probably intuitive, but I'm just put in here to make sure. So we have three instance classes here. These are, yes, sorry, question.
Sorry to backtrack a little bit. You kind of touched on OOPs, I think around 3 times so far.
Yes.
I was wondering if you could give a couple examples of what those might be.
So an OOP is an ordinary object pointer. So we've encapsulated that as a C++ in Hotspot. So when you see anything that says OOP, that means it's a pointer to an object. And then if it has something after it, like you would normally see instance OOP, would be a pointer to an instance OOP-desk. Instance OOP-desk is the class that describes the structure of an instance object, and an instance OOP is a pointer to that.
So that's a specific list of classes that are essentially implemented in C++, but it's exposed as Java classes to the runtime?
Correct, yes.
So that would be what, Java lang integer or?
Precisely. Yep. So yes, bootstrap classes as well as user-defined classes. All of those are represented by these kinds of C++ classes. Okay, so we have 3 classes that are shown here. There are 3 instance classes. We have a superclass, which defines a field called A. And in the process of loading this, the hotspot has decided that every instance of this class is going to have field A at an offset of 8 bytes from the beginning of the object. We have 2 subclasses. The one on the left defines 2 additional fields, B and C, and they're assigned locations 12 and 16 in any instance of that particular class. Subclass on the right defines another field, different field, D, which happens to be assigned another offset of 12 bytes from the beginning of the object. So the upshot of all this is if we encounter an object of any one of these 3 classes, we always know that field A is at offset 8. So superclasses are always prefixes of their subclasses in the way objects are laid out. Does that make sense? So if you run into a subclass, you know exactly where to look at for fields that are defined by a superclass. Okay. Template interpreter. How am I doing on time? Oh, not too bad. Okay. So a typical interpreter has what we call a fetch switch exec loop. So normally an interpreter would pull out the next word or bytecode or whatever it is that it's interpreting. It would then go through a humongous switch statement and say exactly what did I just pick up, and then would branch out to some other routine to actually execute that code. The template interpreter, Hotspot's template interpreter, doesn't do that. Okay, now I'm dating myself here. Are there any 4th programmers here? Nice! Rock on. All right, so it's very similar to indirect threaded code in Forth, where basically we pull out a byte and then we index into an array which has a dispatch directly to the thing that we're going to do. So it's a squished down version of a switch table. And it's called a template interpreter because we actually start this out with a platform independent template which describes every one of the Java bytecodes. It describes what kinds of conditions are expected on the stack when it begins and what kinds of conditions are left on the stack when it finishes executing. And so at runtime, which may seem like an unlikely time to do this, at runtime that template is converted into platform-specific code, which then forms our dispatch table. What that means is that the template interpreter has a built-in, written in C++, macro assembler for each platform. So you find these weird things where you have C++ methods that have a whole slew of assembly code, which are actually calls out to other C++ methods, which are part of the assembler, and those actually deposit the specific instructions for the platform into the code buffers. So when you run into these definitions in the template interpreter and you see all this assembly code and you go, what in the world is going on? That's what it is. The template interpreter maintains a single word top of stack cache in a register, and that saves us from having to actually go to the operand stack in a particular frame. And if you've looked at bytecode at all, it repeatedly either pulls something off the stack or pushes something onto the stack. Well, we try to keep that as often as possible in a register so that if a bytecode creates something in the top of the stack and then the very next bytecode or a subsequent bytecode actually looks at that value, which it often does, then we already have it in a register. We don't have to do the 2 memory operations to push it and pop it. And then finally, because the template interpreter is an assembly language and it's limited in what it actually can do, there's several escape sequences to call out to the JVM itself and say, help, I need you to do this for me. I need you to allocate a really large object for me, or things like that, which are difficult to do in assembly. Okay, so we mentioned the top of stack cache state. I'm going to go into this in just a little bit of detail because it's a little bit confusing. So there's an enumeration within Hotspot which tells the interpreter at any given point in time what state this top of stack register cache is in. And so there's these multiple values here that represent all 8 of the primitive types that, all 7 of the primitive types that Java defines, and an 8th type, which is the ATOS, which is basically an object pointer. It says that this top of stack register cache contains a pointer to some object, could be an array, could be anything else. And then finally, there's a state that represents there's nothing cached currently. So here's the class that actually defines the template, which, again, I told you we start out with a template table, a template for each possible bytecode. And so this is most of what the template contains. So there's some flags and stuff, but most importantly, here's this TOS state. So this is the top of stack register state that bytecode is expecting when it begins execution. And then another value indicating how it's going to leave things, whether it's going to leave something in a register and what type it will be or not. So the way that's used is here. So over here on the lower right, we're executing a method. We're right in the middle of some bytecode. We run into these 2 bytecodes, X and Y. And so we know that bytecode X leaves an int on the top of the stack, and bytecode Y, immediately following it, happens to consume an int. Well, that's exactly the kind of situation that we go through all this bookkeeping for. So here's our dispatch table as we construct it after we work through those templates. And it's a 2-dimensional array indexed by the bytecode value, as we mentioned, the indirect threading code, as well as the top of stack state that the previous bytecode left things in. So here's our assembly representation of our assembly instruction that executes bytecode X. And the very last thing it does here is it goes, as an interpreter should, it gets the next bytecode, and it finds the ITOS entry because, again, bytecode X leaves an int on the top of the stack. So it's going to look through here, find this leftmost black box or pointer, and so then we'll be able to jump straight into the assembly code for bytecode Y, which immediately starts executing this stuff based on an int being in the register. Okay? Making sense? If, however, the bytecode prior to Y didn't actually leave an int in that register, say it left nothing in the top of stack cache, then you would actually have to go through execute the very beginning, the preamble piece here, where it says pop int, where we would actually go to memory and pop the first value off into a register, and then we can proceed with the same common code. Okay, good. Took me months to figure this out. All right. Okay, so as we're executing, we run into method invocations, and the interpreter has to manage the stack. So over here on the left is a representation of what the stack will look like. Stack is growing up in this case. So before we have an invocation, we have our local variables, which are the parameters that were passed into this particular method, as well as the local variable slots that had to be allocated for its execution. There's a save area, which is a bunch of platform-specific stuff, return addresses, frame pointers, the previous bytecode pointer, stuff like that. And then the hotspot interpreter maintains an operand stack where operands get pushed onto and popped off of as the bytecode requires. So now after we do our invocation, our method invocation, all of the stuff on the bottom is pretty much the same. That save area is maintained. The operand stack, which was active at the point of this method invocation, is also saved. But the calling method has pushed a number of parameters on the stack. The called method will allocate a number of additional locals on top of that. It'll save the context of our previous method invocation and establish its own operand stack on top of that. Okay, so the good part of all this is that these local variables are kept in a single contiguous array, so as the bytecode hits them and asks for the value of local variable 3, for example, we know exactly where to go and find it on the stack. Okay? All right. So threads. So Hotspot maintains a one-for-one threading model in all the platforms we run on, which means that a Java thread corresponds to an OS thread, which corresponds to a hardware thread. So if you've got a multi-core machine, then all of our platforms are able to take advantage of that. So those define threads at the OS level, and Hotspot maintains a one-for-one relationship with those. So there's a hierarchy of thread types that Hotspot maintains. They're shown here. I've highlighted two in red. VM thread is a special thread within Hotspot, which does special operations that different threads request. In particular, the call out to a VM thread from an ordinary executing Java thread can ask for things like a safe point. So you can bring the whole VM to a consistent state, so you can then do interesting things like garbage collection is one, or stop the world garbage collection. But you can also do things like traversing different thread stacks to see which methods are actually being invoked, so you can collect information about them and figure out which methods need to be compiled. Java thread, here in red, is the representation for all actually executing Java threads. So one operation that Hotspot threads do frequently is try to find their thread object. So typically the way you have to do this is you actually have to go to the operating system and say, hey, OS, what thread am I? And it gives you back some kind of thread identifier. And then you got to look that up in some table to actually find the internal thread object, and then you can manipulate that. So what Hotspot does is it defines platform-specific ways of tracking this down very, very quickly. The reason we need to do that is because threads very often will do things that are thread local. For example, allocating small objects, we try to do in a thread local fashion so we don't have contention for a memory pool if all the threads were all going for one place. So we assign pieces of the heap to each thread so they can actually manage that independently, and that's kept in this, or at least pointed to by this thread local storage thing. So threads, as they're executing, will hit this very, very often. I need to allocate an object, I need to find my little piece of the heap, and then it can do it. Okay? So we maintain a singly linked list of Java threads. This is just a representation here. It's the head of the linked list is a class called threads, which contains only static variables. So you can actually, if you're debugging or stepping through Hotspot execution, this is the way you can find your way to the list of Java threads. Each thread object points to the actual Java object that represents that thread. So there's an internal C++ object that represents a thread, and then there's the actual thread object on the heap, which you can do things with as you're executing your program. Okay? Make sense? Okay, so this is how this whole thing fits together. So we have multiple Java threads. They execute through the interpreter, and as they're executing through the interpreter, through this dispatch table, doing the fetch next byte code, jump through the dispatch table, they're accessing the metadata that we've loaded in the class loading part, which we talked about at the very front of this, and they're accessing the heap and modifying and creating objects. So that's kind of the big picture view of how Hotspot fits together, and those are kind of the primary components. So that's what I have for you today. I am open for questions at this point. Is this crazy? Yes, question back there.
Just a quick question. Going back, I'm still trying to figure out all that stuff you're saying about the interpreter. So if bytecode X leaves an int on the stack, and then bytecode Y, the next bytecode, you gave the example of it doing a VTOS entry, so copying the thing off the stack. Or what happens if bytecode Y takes a double? Will X dispatch to a DTOS thing that will convert the into a double, or what will it do?
Right. So if we execute bytecode Y, and the previous bytecode has, for example, left it. I hope everybody heard that question, by the way. If the previous bytecode had left, for example, a float or a double on the stack instead of an int, then these pointers over here in the dispatch table would point to an error routine, which basically says this is not a valid state. We've got We have an invalid, we have a type on the top of the stack which is incompatible with this bytecode we're about to execute. And so then we throw an exception in. Yes, you first. The verifier should do most of that, and it's not necessarily, I mean, the check is free, right? We have to do a pointer lookup anyways, and we don't actually expect this to happen, but if you're going to look up a pointer, you have to handle that situation gracefully. So yes, you're absolutely right. It's normally caught by the verifier. In the red, please.
About class loading, just if that in a job file has the happily just same package, same class name, and twice in the job file, is that only first one get loaded in the system, and second one whenever it has chance to load in the system?
You mean if you have two classes in a jar file with the same name?
Same package name, same package name, same class name.
Same class name. I think it would normally, yeah, just load the first of those. Yes.
Do you think is it a feature or is it a kind of a bug?
Well, can you give me an example of why you might want to have?
Because we do not want to have two, but it just happily had for the naming convention, we do not communicate very well.
Yes.
And somebody just happily has same name, same package name, same class name, and they're loading the system, and then so suddenly my previous class doesn't work anymore. That's okay, just loading order.
Yeah, sure. Some unexpected loading order. Yeah, it would be good to have that as an error. I mean, what Hotspot does is it actually memory maps each jar file, so it knows exactly where to go in order to find things. But it does not scan for duplicate class names. Yeah. Sorry?
Jar signing helps with that, though.
Jar signing would help with that. Yes, absolutely. Yeah. Yes.
So with this, which is shown right here, it only holds the top of stack in a register. You don't have like the last 4 entries or anything like that. Nothing.
Correct. Just one.
Intricate.
Yep. Yep. And that's where the hottest activity is at the top of the stack. But yes. And I mean, it could be a future improvement for us to do multiples. Obviously, it would take major surgery to do that on this, but we've also had to execute on platforms like x86 who just give you pittance of registers. So yes, in back.
For someone trying to learn the OpenJDK or the Hotspot code,
Yep.
are there some projects that you took on, just as maybe even hacks that you did to the code base just to try to learn it? Can you give some examples of some things to try out just to kick the tires?
One of the things that I started out doing and still enjoy doing from time to time, just to figure out what in the world is going on, is to create your own little class that ultimately calls out to some sort of read operation that blocks. And so having done that, you can then attach a debugger to it, and you can see how the stack is all lined up when you've hit this read operation. And then you can start poking at pointers and say, oh, okay, there's a save area for that frame, and then there's a save area for that frame. And you can actually return from that topmost read operation and then start stepping through bytecodes, for example, if you wanted to with the interpreter. So that's a really good way to start. And then if you have complex operations that happen as part of that, like allocation of another object or something like that, then you can actually start tracing those through the parts of Hotspot. Good question. Yes?
How are exceptions handled? I mean, are exceptions marked on the stack? Java exceptions?
Java exceptions are marked on the stack, yes. And then as you hit an exception condition while we're executing, then we roll back the stack looking for the particular mark. Okay, as we process a class file and process the bytecodes that are associated with a particular method, there's if you ever used Java P to disassemble a Java class, so at the bottom there's an exception table that gets encoded in, and we basically just roll back the stack looking for the place that's supposed to handle a specific exception. Yes, correct. Yes.
Are you talking about the Java training model 1:1:1?
Yes.
Let's say if you're running Java on any of the Linux system, And when you create a new thread, isn't it just creating a new Unix process? And and while your thread is doing whatever operation, that process is in user space or kernel space, or do you really create? Hey, this is you were saying 1:1. It's 1:1 is really like processor thread and a Unix process that's running in user space and kernel space. Is there a mapping, where did you essentially, did you really map, hey, this Java thread maps to this Unix process, or it is just a Unix process operating in user space and kernel space?
Correct. Yes. So Hotspot occupies a single memory context. So every thread can see all of Hotspot memory. And when you create a new thread, we actually ask the operating system on Unix or any other platform, we say create a new thread for us. And that means that we've created an OS schedulable entity, but it has the same memory context. Does that answer your question? I think not. Kind of.
Unix really creates a process. You map that to thread to the process.
Right. So in the old, on Linux, for example, the old threading model said that you actually execute a clone operation, where you specify what's going to be in common between the new task, Linux. Correct. Yes. Yes. Other questions? Yes.
How much of the JVM would you say is written in C++? Is it a big percentage, a small percentage?
Oh, big percentage. Yeah, vast majority. Yeah. But these template interpreter snippets are technically written in C++, but they have callouts to C++ method names with things like LD, and so it's an assembler language embedded in C++. Yes.
Is the profiling information, is that gathered in line in the interpreter, or is that done in a separate thread? You're thinking about, I think, stop the world of save points.
Sorry, what information?
So profiling information.
Oh, profiling information.
Is it done inline in the interpreter mode?
Let me think about that, profiling. Yes, so normally profiling would be done as we invoke a new method and we would make a little mark. It's actually, yes, so it's actually inline in the interpreter assembly code. So what the interpreter attempts to do in many cases is, although there would be a simple way to do a particular operation, like, for example, find a method structure that represents a particular method and increment a counter in it. It would be easy to do in C++, but what the interpreter attempts to do is to do that in sort of unwound assembly language. So that you see these things like, okay, find the method structure and what is the offset of the invocation counter within the method structure. Find that, increment it using the assembly instruction and store it back. So that's the kind of, and similarly for manipulating the heap, it'll actually allocate an object modifying the heap data structures. So it's some of the assembly stuff gets pretty ugly, but it's supposed to be fast. Yes.
Yeah, so the thread dump also requires save point. Taking thread dumps, does that require save point?
Thread dump, yes, does require a save point. Yep. Yes. How does Hotspot do optimization? That is a very... Okay, so there is a linkage. As we maintain entry points to methods, we actually maintain 2 entry points, an interpreted entry point. So if you're entering that method from an interpreter, then you use one of those entry points. If you're entering it from compiled code, you use the other entry point. And the reason for doing that is to allow us to switch back and forth, because the compiled code uses different calling conventions than the interpreter does. So we have to do these kind of, if you're in interpreted mode and you call a compiled method, you've got to tidy up the stack a little bit before you call the compiled method, and vice versa if you're going back to interpreter. That could be quieter. Holy moly. So was that what you were asking? Yeah. Yes.
Actually, just verification from yesterday's keynote announcement that mission control and the flight recorder getting to the Oracle JVM or still in the JRocket?
No, it's in Oracle now.
Oh, okay.
I think our first release of it was like 7U40 or something like that.
Oh, okay, that's good. Second question.
Yes.
Is there any plan that Oracle database JVM will using that current Oracle JVM?
Will the Oracle database start using the Hotspot? Oh, you mean the?
Hotspot, yes, the Hotspot, yeah.
Uh,
Does Oracle has any plan just using same JVM?
Well, Oracle uses. You mean as opposed to JRocket? Or
Actually, Oracle's database itself has a JVM that is long time ago. It's Oracle JVM.
Bundled with it.
Yeah.
It's a separate install.
I see.
It's one release behind. It's still HotSpot.
Yeah. Forgive me, we're a little siloed here, but yeah, there's a lag time, as you might guess, between the release of an update of a JVM and when it's adopted by other projects, WebLogic and Coherence and all the other dizzying array of products that Oracle has. Yes?
You mentioned that threads may keep their own heap of objects that were allocated locally that didn't leak outside of the thread.
Yes.
How does the time to clean that up occasionally for garbage collection compare to the cost of just killing a thread and making a new one?
Killing a thread and making a new one. And
Would it be better to have a long-lived thread that has a thread local cache that needs garbage collecting a lot, or shorter lifetime and killing the thread so that you can just dump the whole heap of thread local objects and start again?
so the thread-specific garbage collection algorithm is very quick. We've basically allocated these objects linearly, and we can keep track of all the references from the rest of the heap to that small array of objects. So that's a very efficient operation. I wouldn't think that creating another thread would buy you much, if anything. Yes, in the back.
What is Oracle's direction between JRocket and Hotspot? I mean, which one is where the energy is going? What is the...
So JRocket is basically in maintenance mode, right? It's still on JDK6, and there will never be a JDK7 release of JRocket. What we've been doing over the past 2 years or so is gradually taking some of the interesting and useful technology pieces out of JRocket and migrating them into Hotspot. So Flight Recorder is a perfect example. Okay? All right. Well, thank you very much. Thanks for coming.